Okay, time for some examples of finding asymptotes of certain functions. If you have taken a math class recently where you had to find all asymptotes of rational functions, such as college algebra or pre-calculus, you might feel confident enough with this type of problem that you can skip over this video. However, if you have any doubts about the process, or maybe you just like to make sure, I'd recommend that you keep watching. Okay, so we're going to start out with finding all the asymptotes of the function y equals x plus 2 over x squared minus 4. Okay, now we're going to run through our three different types of asymptotes here and see if we're going to have each one in the first place. And then if we have that type, we'll find its equation. So we'll start with vertical asymptotes. Those are often the quickest for us to find because we've seen them for the longest usually. These get introduced back in algebra, and so we're usually fairly familiar with this process. So remember, for vertical asymptotes, you are going to set your denominator equal to 0 and look for factors that cannot be canceled. Okay, things that can't be canceled out, because if it can get canceled out, that's just going to be a hole in the graph. Okay, so we're going to take our denominator here, x squared minus 4, set it equal to 0. And to solve that, we will factor. Okay, x plus 2, x minus 2 equals 0. And then you would set each factor equal to 0 to get our results. Okay, whoops, went a little too fast there. All right. So we're going to end up with x equals -2 and x equals +2 as potential vertical asymptotes. Okay, so we need to check on these and see which one of those factors could be canceled out and which could not. Now, in some cases, neither factor will be able to be canceled, and they're both vertical asymptotes, and that's fine. In this case, one of these factors can be canceled, you might notice. X plus 2 could be canceled out when we factor. So this factor, x plus 2 here, is actually just going to cause a hole in the graph when x equals -2. So let's note that. So this can be canceled. So this value here creates a hole in the graph rather than a vertical asymptote. So our vertical asymptote here is just going to be the second line or value from the factor x minus 2. Vertical asymptote is x equals 2. And notice how that is already in the form of a vertical line. X equals some constant. Okay, so there's our vertical asymptote. And now let's investigate our other types. We'll move to the horizontal asymptotes. And for those, remember, we're going to be looking at the limit as x approaches infinity or negative infinity. I like to just start with positive infinity to see what we're dealing with, because it's a little easier for me to think about personally. And then we'll take the limit of our function. Okay, so here we get to practice our limit skills. So notice it's a limit as x approaches infinity, like we've been working with in 2.6. So the trick here is to use our useful theorem And trick number 1, where we divide or multiply everything by the reciprocal of the highest power in the denominator. Highest power is x squared. Reciprocal is going to be 1 over x squared. Okay, so we're just going through that regular limit process from this section. So it's the limit as x approaches infinity. Let's do some distribution here. We would get 1 over x plus 2 over x squared in the numerator. And then in the denominator, we would get 1 minus 4 over x squared. Okay, we see some familiar types of expressions, so it's time to use our useful theorem. These 3 terms, 1 over x, 2 over x squared, and 4 over x squared, are all going to approach 0 as x approaches infinity. Okay. Or you might note they would still approach 0 if this was x approaching negative infinity. As x gets really, really large in either the positive or the negative direction, all 3 of those highlighted terms would still get really, really small and approach 0. So that's why I just like to start with the x approaching positive infinity limit, because often it'll be the same result for x approaching negative infinity. Okay, so we are going to use our useful theorem and replace those 3 terms with the zeros that they are approaching. 0 plus 0 over 1 minus 0. So we have 0 divided by 1, which is 0. Yay. Okay, so we do actually have a horizontal asymptote because our limit approached a constant. So there's our results. Horizontal asymptote is going to be y equals 0. Remember, it's a horizontal line, so we write it as y equals a constant. All right, now we've got our vertical, we've got our horizontal. Slant asymptotes, and remember from our notes that a horizontal asymptote and a slant asymptote will not occur together. Okay, if we were going to have a slant asymptote, this infinite limit, or limit as x approaches infinity, could not be approaching a constant. So we are not going to have any of these because there is a horizontal asymptote. Okay, so there are our results. Vertical asymptote x equals 2, horizontal asymptote y equals 0, no slant asymptotes. Okay, next example, we are going to find all the asymptotes of y equals x squared minus 3 over 2x minus 4. And we're going to go through essentially the same type of process, just kind of checking through our different types, starting with vertical asymptotes. Okay, so we want to set our denominator equal to 0 and solve. Okay, and we end up getting x equals 2. For seeing if that factor or that value is going to cancel out at all, you can usually tell by looking at the function, but if you factor this even, you can tell it's not going to cancel out. Okay, there's our factor down there, the x minus 2 that causes this x equals 2 value. Okay, and then the numerator would be this factorization x plus square root of 3, x minus square root of 3. And you can tell that's not going to cancel anything out there. So We're good. This is a vertical asymptote. X equals 2. All right. Now, let's see about horizontal asymptotes. And if you can spot the shortcut here, you can certainly use that. I'll just go through step by step here. Horizontal asymptotes, we would want to check our limit as x approaches infinity of our function. Okay, and we would use our trick here, multiplying by the reciprocal of the highest power of x in the denominator. So highest power is x. So we would multiply everything by 1 over x. And that would give us limit as x approaches infinity. Let's distribute. Get x minus 3 over x. And then we would have 2 plus 4 over x. Okay. Now these two terms, 3 over x, 4 over x, those are going to approach 0. But notice we have one term that is decidedly not going to approach 0 and not going to approach a constant, the x right here. So as x gets very, very large, that is not going to chill out and go away for us. That is going to get bigger and bigger. Essentially, we're looking at like x over 2. As x is really large, dividing it by 2 doesn't have much of an impact. It's still going to be a really huge result. So this is going off towards infinity. Okay. So that fact that it is not approaching a constant tells us that there is no horizontal asymptote. Okay. So as x approaches infinity, the function also approaches infinity. And now we're going to see if there are any slant asymptotes. Okay, that might tell us about that behavior. And check it out. Our function, rational function here, has a numerator that is 1 degree higher than the denominator. So if you spotted that before we started looking at the horizontal asymptotes, that's the shortcut. You can tell because of the degrees that there is going to be a slant asymptote here. So if there's a slant asymptote, there can't be a horizontal. So you could just use that to justify the fact that there are no horizontal asymptotes. Okay, so yes, there is a slant asymptote. I'll write that just to show us, yes, because numerator is 1 degree higher than denominator. Okay, numerator is degree 2, denominator is degree 1, check, check. Okay, so how we are going to find the slant asymptote is through polynomial long division. Good times. So we are going to take our numerator, x squared minus 3, and we are going to divide by 2x minus 4. Now, when you're setting this up, if there are any powers of x that are missing in your polynomials, you'll probably want to put some placeholders in. So notice how our numerator is missing an x to the first power term. We're going to put in a placeholder for that. It'll just help keep your problem better aligned, and it'll make this process easier to do. So we're going to write x squared plus 0x minus 3. Okay, so I'll make a little note there to use a placeholder for any missing degrees of x. It'll help, seriously. Okay, so when we do this, it's a lot like doing division, long division, back in the day when you learned arithmetic long division. You might have taken something like 683 and divided that by 3, let's say. Um, so the process here, if you remember, was to say, okay, how many times does 3 go into 6? And you would say 2. Or another way of thinking about that is, what do you have to multiply 3 by to get 6? The answer is still 2, but that's going to come in a little handier for us in this polynomial long division to think about it in that second way. What do you have to multiply this by to get this? Okay, so how we're going to use that here is saying, what do we have to multiply 2x by to get x squared? All right, so think about that. What do you have to multiply 2x by to get x squared? Well, you would need an x for sure. And then to make the coefficients come out right, we would need that to be 1/2 x. So 2x times 1/2 x is x squared. Okay, so that's why we put that 1/2 x up on top. Okay, and then for our next step, let's go back to the like long division problem over here. Remember, back in the day, you would take this value, multiply down. So you'd say 2 times 3 equals 6, and then you would subtract that off. All right, 6 minus 6, 0. And then you would bring things down. Bring down your 8 and your 3. Okay. Keep erasing the wrong things here. Okay. So we're going to do that same thing in our polynomial long division. Multiply down, but remember to multiply this entire polynomial when you do. So we're going to multiply 1/2 x times 2x, and that gives us x squared. And then 1/2 x times -4 would be -2x. And we're going to subtract that from the previous line. Okay. And when you do that, make sure you distribute that negative. X squared minus x squared zeroes out. That's good. We wanted that. And then we have this 0x and plus 2x. That's why we use the placeholder there, because it lines things up better for you. You wouldn't be trying to like add the 3 and subtract 2x or something like that. So placeholders are very handy here. Okay, so let's see what our next step is. We'll bring down this -3. And now let's go back to our long division with numbers. Okay. Your next step over here would be saying, okay, how many times does 3 go into 8? And we would say that goes in twice. Okay. And so over here, we're going to say, how many times does 2x go into 2x? Or, you know, the other way of thinking about it, what do you need to multiply 2x by in order to get 2x? In either case, your answer is going to be just 1. So that's what we need to put up on top here, a positive 1. Okay. And once you've done that, we're going to follow the same procedure. Multiply down, okay? In the long division here, 2 times 3 would be 6. Subtract it off. Okay, we'd get 20 and then 2 and bring down the 3, okay? And over here in our polynomials, we'd need to do 1 times 2x plus, or sorry, 2x minus 4, right there. Make sure you distribute to both terms, okay? So you'd get 2x minus 4, and we're going to subtract that off. Okay, 2x minus 2x would be 0, that's good. And then negative 3 minus negative 4, so watch that double negative. Okay, negative 3 plus 4 essentially is plus 1. Okay, now in our long division with the numbers, we would have to keep going here. How many times does 3 go into 2? None. Okay, how many times does 3 go into 23? Okay, that would be 7 times. And then you would multiply down. 7 times 3 is 21. And then you'd subtract. And then you'd get to this point where you're saying, okay, how many times does 3 go into 2? It doesn't. And then you'd say, okay, I'm done. And this is my remainder. Okay, remainder. And then you'd have your quotient up on top here, 227, and then a remainder of 2. All right. Now over in our polynomials, we'd be saying here, okay, how many times does 2x go into 1? Well, maybe let's think about that as like, okay, what would you have to multiply 2x by to get 1? And the result would be, well, 1 over 2x, but we're not going to put that up in the quotient up here because we are essentially done now. You get to stop this polynomial long division process when the remainder down here is of a lower degree than the divisor. Okay, so stop here. Okay, this is your remainder. All right, so when the power of this remaining portion down here is lower than the power of the polynomial that you're dividing by, that's when you stop. Okay, and so we have our remainder of 1, and then we have a quotient right here of 1/2 x plus 1. And so that, notice, is a linear expression right there. 1/2 x plus 1, that is linear, like an mx plus b type of situation. And so this quotient, this is the equation of the slant asymptote. So this gives you the equation of your slant asymptote right there. It spits out automatically, which is really cool in my opinion. So our slant asymptote for this function is going to be y equals 1/2 x plus 1. And now we've got all the asymptotes for this function. One vertical asymptote and one slant asymptote. So there we go.